Hi, I'm Robyn Speer, and I'm going to be talking about how text breaks and how to fix it. So, Mojibake is the phenomenon when text ends up with the wrong Unicode characters in it due to an encoding mistake. And ftfy is a Python library that I developed over several years that understands in several cases how to fix these characters. So, here's an example of what ftfy can do. It can take this mess and understand it as the French sentence that it was actually supposed to be, even though one of the words got extremely mangled. So let me introduce the mascot of ftfy, who is this little guy. This actually comes from this text that I found in the wild. And if you use ftfy to decode the multiple layers of mistakes that happen to this text, you can see the face that it was actually intended to be. And I like this guy because he's giving you a really you can do it face. And it's the result of actually decoding some very messed up text. So let's go back to a simpler time when one byte represented one character. And this meant that there were at most 256 possible characters of text that you could represent on any given computer. And let's hack up some quick Python code that's going to show us tables of these characters. So a very straightforward character table is called ASCII. And these are 128 of these characters that we agreed on back in the 60s, and we can all agree on what byte corresponds to what character as long as it's one of the 128 characters in ASCII. And if it's one of the other bytes, then ASCII just doesn't say what it means. And this is a set of characters that works out pretty well, especially if you're a monolingual American. But there are many more things that you're going to do with text, and eventually you're going to realize that you need more characters than that, and especially if you're speaking other languages. So people started talking about the idea of extended ASCII, where we could use the other 128 bytes as characters also. And extended ASCII just means whatever my computer does with the other bytes. And it's going to differ from one computer to another because it could be from a different country, so using a different character set, it could be running a different OS. And this is how Mojibake started. Let's take a look at these different extensions of ASCII, which are called code pages. So a code page you might be familiar with is Windows 1252, which would be used on English copies of Windows. Wait, I missed one. Here's Latin 1. This is a very straightforward code page because it's the first 256 characters of Unicode. And so it's very easy to implement by accident. If you don't really know about Unicode and you just replace every byte with the Unicode character with the same number, you end up getting Latin 1. And I labeled two of these rows as Here Be Dragons because those are two rows of the table that are full of control characters that nobody ever agreed on what they do, even when it became an ISO standard. And Windows 1252 fills in those rows with more punctuation characters, curly quotes, bullets, things that ended up being useful on Windows. But that's only on Windows. If you were looking at the 256 characters you have available in DOS, then you would end up with this different character set, which has all these line art characters in it, and yet another character set if you're using Mac OS Classic. And if, for example, you had a Russian version of Windows, then you have this character set, which has the Cyrillic alphabet in it, which is, of course, very important for writing in Russian. So clearly the situation is unsustainable, and Unicode came along and said, hey, it turns out there are way more than 256 characters. But Unicode was originally hard to use because it wasn't compatible with ASCII. And UTF-8 is a great idea, which is, what if we leave ASCII alone, and instead of using those 128 other bytes as just 128 more characters, what if we use them as a variable length encoding for the entire rest of Unicode? And there are some really great ideas in UTF-8, such as not overlapping with ASCII ever, and also being self-synchronizing. It's got patterns in its bytes that tell you where each character begins and ends. And so if you jump into the middle of a UTF-8 string, you can tell where the start and end of each character is in the bytes. And so everybody adopted these great ideas and used UTF-8, right? Well, no, of course, it's not that simple, especially because Microsoft had just done all that work to make Windows support Unicode, and all of their APIs use UTF-16, which is more difficult to use. And so this provides more opportunities for Mojibake. So let's have some more code that's going to show us the sequence of bytes that represent each character in UTF-8. So if you take this name, L'Hôpital, we can look at it in UTF-8, and the simple letters that are ASCII letters are single bytes, but this curly quote turns into 3 bytes, and the O with an accent on it turns into 2 bytes. And so if you've got text that's in UTF-8, you can encode it as bytes, and somebody else can decode it as UTF-8 and get the same text. But if they decode it as a different character set, then they're going to end up with something like this, with a bunch of miscellaneous symbols in it that weren't intended, and that's Mojibake. And any mistake that you can make with a computer can also be repeated. So you end up with these pileups of Mojibake where the same encoding and decoding mistakes get iterated. And the fortunate thing here is because of the self-synchronizing nature of UTF-8, we can recognize the patterns that it leaves behind, because the patterns of bytes that make up UTF-8 show up as distinct patterns of characters in the Mojibake. So this second string here with all of the square root signs and not signs in it is sending us a huge signal that, like, hey, this is actually supposed to be UTF-8, but it came out in macOS Roman. And when we see a pattern like that, we encode as whatever the other encoding was and decode it as UTF-8 and presumably get out what the text was expected to be. So we can take that example and we can decode it, encode it as Mac Roman, decode it as UTF-8, and get this, which is still Mojibake, because it turns out that we need to do that again, and we need to do it again. And after decoding 3 layers of Mojibake, we get the text that was intended. But this is a job that the computer can do for us. So here's some code to use ftfy and format its output nicely. And we can put the text into ftfy. And so the first example here, it shows us that what you need to do with this text is encode it as Mac Roman and decode it as UTF-8 3 times. In this other example, it turns out that all of this Mojibake was just 1 apostrophe, and you need to encode it as something like Windows 1252 and decode it as UTF-8 3 times, and maybe even uncurl the curly quote at the end if you want. And this is an example I love because they said, I just figured out how to tweet emojis, and then they hadn't quite figured out how to tweet emojis because they're tweeting through something that used a broken implementation of UTF-8 and also somehow came out as Latin 1 instead. But if we recognize that, we can figure out what the emoji were actually intended to be. Now, we can't just apply this to every string that looks like it could have been UTF-8, because we don't want to have false positives. There are combinations of symbols that could have been UTF-8, but are actually what you meant in the text. So you could be writing in capital letters with accents next to punctuation, or you could actually be talking about the square root of pi, and we don't want to replace every instance of one of these with a different character. You would get examples that are wrong, like these down here at the bottom of the screen. So it's important for Mojibake to have a regular expression that can detect when something is likely to be Mojibake. And so we call this the badness metric. And so it looks for things like these improbable combinations with accented letters next to particular currency signs, or maybe unpopular punctuation like the Pilcrow sign next to another character that comes from one of these character sets. And with this big regular expression, we can recognize patterns like this. So in this string, 3 out of 4 of the instances of Mojibake match the regular expression, and they all have the same explanation for what went wrong with them, and we can use that to just fix the entire string. So this is a heuristic that I've been hand tuning for several years, and people have asked me, well, you know machine learning, why doesn't ftfy use machine learning? And I don't think I'd be able to keep the rate of false positives this low using machine learning. It's very hard to explain to machine learning the idea of an error rate of once in several gigabytes of multilingual text. And also, in my experience with language models, they have a tendency to kind of homogenize text to make it say what they expect it says instead of what it actually says. And I don't want to do that. I don't want to cause more problems using ftfy. And so that's why I tune it by hand instead of using machine learning. But let's talk about some of the root causes of Mojibake. And I identify 3 causes that I encounter over and over. One of them is Microsoft Excel. The second one in general is programming language APIs that confuse you about how to use Unicode and let you mix up bytes and text. And the third one that I run into a surprising amount is an outdated heuristic called Chardet. Let's take a look at that. So Chardet originated as part of Netscape Navigator in 1998. And in the 90s, because there were all these different code pages that people were sending around text in, you needed to be able to guess based on completely unlabeled bytes what encoding it was in. The problem is that the assumptions come from the 90s, and these assumptions aren't necessarily true anymore. Chardet doesn't know that the correct answer to what encoding is this is usually UTF-8, and it's never seen an emoji. So if you show it the bytes that make up an emoji, it thinks that there's some kind of Turkish. But the biggest problem is Microsoft Excel, because there have been so many different ways to export supposedly plain text CSVs from Microsoft Excel over the many decades of its existence, and Microsoft never breaks backwards compatibility with anything. So if you're trying to export a CSV, you have all of these options for how you could export text from Excel. And if you want to use UTF-8, every single one of these options is wrong, even the one that says Unicode text. And I know that you might have to use Excel sometimes, but if you want to make a CSV file to have comma-separated plain text, I strongly recommend that you use LibreOffice or Google Spreadsheets instead, because they can handle UTF-8. In general, I've got a recommendation for how to avoid Mojibake being produced by your code. Because if you use English a lot, you might go for a long time without noticing Mojibake because all the ASCII characters are still right. But the good news is emoji are everywhere, and people expect them to work, and they are a really good test of your Unicode. So my recommendation is use lots of emoji. Put them in your code, your UIs, definitely put them in your test cases, and make sure that they come out right. And it won't even look weird because people use emoji all the time anyway. This is similar to the way web frameworks used to put extra parameters in the URL, like snowman equals this picture of a snowman, because then the web framework could make sure that the browser had to use UTF-8 and detect if it came out wrong. And that's what I've got to say right now. Here is some extra information about ftfy and about myself. Thank you.